Agriculture is a sector that plays a major role around the world, especially in Southeast Asian countries. According to UN country data, from 2005 until 2012, the growth rate of Southeast Asian rice imports reached 14%, making Southeast Asian rice trade a major contribution to the growth of rice trade in the world rice market. The high demand for rice in Southeast Asia also requires effective methods to operate water irrigation system, which is the key to the growth and production of paddy rice. Water availability greatly affects the growth rate and production of rice. Therefore, water must always be available so that the growth of rice plants is optimized. Nowadays, the limited availability of water causes farmers to innovate to overcome this problem. One of the farmer innovations is to form an agreement consisting of owners of rice fields with one small water volume irrigation source. They will also take turns closing the main irrigation temporarily to block water and speed up the filling of water into the rice fields. Farmers still manually close and open their rice fields. Overcoming the problem of limited water also requires more effective and efficient irrigation management. From this problem, we from the outer proudly present a solution with our irrigation system tool innovation, which is Aquasaver. Aquasaver is an innovation by developing rotating water use management with an automatic control system to meet the water needs of rice fields from upstream to downstream. The difference between this tool and the others is that it focuses more on regulating rice field irrigation using a variable water level height-Q control and a safe limit range. From this advantage of Aquasaver can be very useful for farmers today because it can streamline time and water usage.
This manufacturing process begins with designing the tool and designing the homogeneous water valve, which will be automated. Then proceed with making the tool scheme, and the last step is to assemble the tool according to the design made. In this tool, the main components are divided into two, namely the communications component and the motion component. This tool uses Node MCU ESP8266 as a microcontroller and SX1276 series as a radio frequency for communicating tools from the server to the direct tool, using a DC motor as a valve drive and ultrasonic sensor as a drive sensor. The drive concept using the Romigen concept. The method of this tool is the flow of irrigation water from upstream is temporarily closed to fulfill the rice fields in the first upstream. If the first upstream rice field is sufficient, the irrigation flow to the first upstream rice field is closed. The flow of rice field from upstream is open, and the flow of water after the second upstream is temporarily closed. So, the irrigation waters fills the rice fields in the second upstream, and so on until downstream. This research used a simulation of 3 rice fields. Each rice field has 2 control blocks, namely the main irrigation flow control block and irrigation flow control to the rice field. The main irrigation block has the task of measuring the water level in the main irrigation system and controlling the main irrigation valve. The main irrigation block will close the valve if the water in the main irrigation is less than the lower limit and the water in the rice field is less than the lower limit set by the farmer. Meanwhile, the rice field irrigation block has the task of measuring the water level in the rice field and controlling the rice field valve. The rice field irrigation block will open the valve if the measured rice field water is less than the lower limit of the rice field height setting. This research used a queuing system to organize rotating irrigation. The first rice field is given Q1, the second rice field is given Q2, and the third rice field is given Q3. The rice field server block will manage this Q number. The tests carried out in this study are ultrasonic sensor testing by comparing manual measurements data with sensor measurement. Then automatic mode control testing with queuing is carried out using an algorithm experiment with a repetition of 3 times, and valve door testing is also carried out. Ultrasonic sensor testing was carried out on the 3 rice fields. In the first rice field, the distance measurement was obtained as high as 125 millimeters. During the experiment, the sensor detected a measurement value with an average of 125.292 millimeters. The sensor detected the highest measured value was 125.8 millimeters, and the lowest was 125.19 millimeters. The following diagram shows a stable measurement. The error value obtained in the first rice field measurement is 0.403%. Then, in the second rice field, the distance measurement was obtained as high as 123 millimeters. During the experiment, the sensor detected a measurement value with an average of 122.5 millimeters. The sensor detected the highest measured value was 122.6 millimeters, and the lowest was 122.4 millimeters. The following diagram shows a stable measurement. The error value obtained in the second rice field measurement is 0.233%. In the third rice field, the distance measurement was obtained as high as 123 millimeters. During the experiment, the sensor detected a measurement value with an average of 123.38 millimeters. The sensor detected the highest measured value was 124.1 millimeters, and the lowest was 120.2 millimeters. The following diagram shows a stable measurement. The error value obtained in the third rice field measurements is 1.29%. In testing the algorithm, the first test was carried out in the conditions where the water level was less than the upper and the lower limit settings. In the following table, the first test of all rice fields in the condition of inactive automatic mode, obtaining a Q value of 1. One of the tests turned on the automatic mode. In experiments 2, 3, and 5, obtained Q change according to the active rice fields. In experiments 2, the third rice field is active, obtaining a Q value equal to 3. In experiment 3, the second rice field is active, obtaining a Q value equal to 2. In experiment 5, the first rice field is active, obtaining a Q value of 1. In testing, turning on 2 or more automatic modes in experiments 4, 6, 7, and 8, obtaining Qs according to the most upstream rice fields. In experiment 4, the active rice field was the second rice field, and the third rice field obtained a Q value of 2. In the experiments 6, 7, and 8, the most upstream active rice field was the first rice field, obtaining a Q value of 1. Then, the second algorithm test is carried out in the condition where the water level is between the lower limit setting and the upper limit. So, the value of the Q variable will be in the system default Q, because its active mode will immediately increase the Q value. Based on the following table, the first test of all rice fields in the condition of automatic mode is off, obtaining a Q value of 1. Furthermore, experiments 2, 3, 4, 5, 6, 7, and 8 obtain a Q value of 1. Then, in the third algorithm, testing is carried out in conditions where the water level is more than the upper limit and lower limit settings. The following table shows the first test of all rice fields in the condition of automatic mode off, obtaining a Q value of 1. Furthermore, experiments 2, 3, 4, 5, 6, 7, and 8 obtained a Q value of 1. In testing the positive polarity of the motor with a voltage supply of min 5V DC and negative with a voltage supply of plus 5V DC, the motor moves the irrigation valve up. The upper limiter works by giving a low signal to the upper limiter in contact with the valve switch to stop the motor. The limiter works well in the first motor test up. Meanwhile, in testing the positive polarity of the motor with plus 5V DC voltage supply and negative with min 5V DC voltage supply, the motor moves the lower irrigation valve. The lower limiter works by giving a low signal to the upper limiter in contact with the valve switch to stop the motor. In the lower limiter of the 5 times trial, 2 times trial, the lower limiter does not send a low signal.